To the first session of today's the StatPhys Kolkata meeting. But the first session will be chaired by Christian Maes. Before I hand over to him, I'd like to remind all the speakers and the participants that there are breakout rooms where one can discuss with the speakers after the at the end of the session. So I request all the speakers to wait there for a few minutes, and the participants can join and discuss with the speakers. With this and without any further delay, I hand over to Christian.
Okay, thank you very much, Abig. So I am Christian Maas. I'm chairing this session. The world has turned Thursday, which means Thursday is active particle day, but viscoelasticity is fine with us also, Clemens. So let me invite Clemens Behinger, Professor Clemens Behinger from Constance, to start a session on barrier crossing in a viscoelastic bath. Please.
Yeah, thank you very much. So you can see my screen?
Yes, it's perfect.
Perfect. Okay. All right. So, sorry for switching the topic. So this was originally meant to be an active method talk, but we are currently working on something which is only partially published, and we thought this would perfectly fit into the scope of that conference. I also would like to thank the organizers and also give credits to the people doing the work. So on the experimental side, Felix Ginot, and then we also had a lot of support from the group of Matthias Krüger at the University of Göttingen and Juliana Kaspers. She's working as a PhD student in his group. So this is a very old problem in physics. We all, I think, at some point you enter it in statistical physics. It's about the thermally activated barrier crossing of a colloidal particle here, which is sketched here. And of course, there's a lot of examples where this is relevant, as been already pointed out by Svante Arrhenius. It's very important to describe reaction kinetics in biological but also chemical systems. At that time, he didn't understand the microscopic mechanism, but it was then only Hendrik Kramers who pointed out that the frequency of the hopping of a colloidal particle is proportional to an attempt frequencies times this exponentially dependent factor where delta U is the barrier and kBT is the thermal energy. And this is, of course, has been well studied theoretically, also in experiments. But what we want to do here is we want to go now to a viscoelastic bath. So we want to go from a Markovian to a non-Markovian system. And what I will show you in the next couple of minutes is that this has dramatic differences on such a hopping process. So just as a brief reminder, what are the properties of viscoelastic fluids? Typically, you characterize fluids in such a simple shearing experiment. You confine the fluids between two plates, and then you apply a stress. So you strain the fluid, and let's say you have such a strain profile, such a step-like strain profile. If you have a viscous fluid, it would immediately follow, the stress would immediately follow the strain rate, simply because the relaxation time of the molecules comprising the fluid is very short. However, if you now consider a viscoelastic fluid, for example, a entangled or semi-dilute polymer network or micellar solution, then you see that the stress is lagging behind the strain rate. And you typically find this stress relaxation times on the order of seconds up to several seconds. And this is a clear demonstration that this is a non-Markovian feature. And I would also like to point out that this already happens even in a range where the rheological properties are still linear, right? So this is not only connected to nonlinear rheological properties, but you also find it at very small Weissenberg numbers. So just one slide to show you what is the system we are using. This is our viscoelastic bath. It's a cetylpyridine chloride. This is an amphiphilic molecule, which then forms micelles, as many other systems as well. It forms rods. And in particular, if you add here salt, then you increase the aggregation and the system is forming giant worm-like micelles. This is just a picture here, and I have given you here a couple of characteristic numbers. Of course, they vary a lot. For example, the persistence length depends very much on the salt concentration, also the mesh size, but these are the typical numbers and typical stress relaxation times on the order of might be about a second. Okay, so that's our bath. Now, how we do our double well potential? Well, in our lab, we do a lot with optics. So we use just an laser beam, an infrared laser beam, which is focused here inside a sample cell, which contains the viscoelastic fluid. And this laser beam is deflected here on mirrors, which lead to a linear forward-backward motion. So the laser beam describes a one-dimensional line, and if you synchronize that mirror motion with the intensity, which is controlled by an acousto-optical modulator, then you can, of course, create any one-dimensional intensity patterns as you wish. And what you see here, this is an intensity pattern which eventually leads then to such a symmetric double well trapping potential to a colloidal particle. You see also the colloidal particle. And because the viscosity of the system is about 15 times that of water, of course, and to limit the measurement times, we have made the distance between the minima relatively small. It's about a micron, so it's about a third of the particle diameter. So you have to carefully watch to see really the particle fluctuating between the two wells. Now, this here is then the dynamics of the particle. You clearly see the hopping from the left to the right and vice versa. And we are in equilibrium. And therefore, if you do the probability distribution, you recover the double well potential. And you see here the orange line is just a fit to the superposition of a parabolic and a quartic potential. And so we can very nicely describe that. And the main point is now that we are able, by playing with the laser intensity, to continuously adjust the potential barrier height. So that's essentially what you have to know for the experimental system. Okay, we are particularly interested in the dynamics, and if you are interested in the dynamics, so a typical quantifier is the waiting time distribution, which measures the typical time a particle stays either in the left or in the right well. I mean, we have a symmetric potential, so this is fully symmetric. And if you do that, and if you do this probability distribution of waiting times, then already the first surprise happens, because this is measured here in a semi-log plot, and opposed to what you would have expected according to the Kramer's rate theory, where you have a single exponential decay, you see we have a clearly double exponential decay with two distinct time scales. That the experimental data points are the open circles, and you clearly see that fit very nicely here to this superposition of a exponential with a short relaxation time and one with a long relaxation time. Now, what's even more interesting is to study how the timescales depend on the barrier height. And this is what you see here. You see the upper one, the larger one, ranges between, let's say, 10 and almost 1,000 seconds. And you see when we change delta U, it follows an exponential dependence. Very similar to what has been predicted by Kramer's, but also very similar, and this is the blue dash dotted line, which has been predicted by non-Markovian rate theory. However, we also observe the smaller one, and the smaller one, and that's very weird, is almost independent of the potential barrier. Here you see the relative amplitudes, and you see both amplitudes are important. So that means for the range of delta U values covered in our experiments between half a kVt and about 3 kVt, both amplitudes are of the same order. Now, how do we understand that? Well, we came up with a simple theoretical description, and that's shown here. So our colloidal particle. In the following, I will refer to a tracer particle because that's the particle whose position, whose dynamics we can trace in our. This is just a spherical particle which interacts with the double well potential and which is characterized by a friction coefficient gamma. Now, to mimic the viscoelastic bath, this non-Markovian bath, we simply coupled another particle to it, a bath particle with a friction gamma B for bath, which is connected via a harmonic spring with stiffness kappa B. So if you think about it, this pretty much corresponds to a Maxwell model, which is known to be a good description also for macroscopic viscoelastic properties, where the viscoelastic properties are just described by a combination of a dashpot, a damping element, and an elastic element. Now, with that model, you can immediately write down the equations of motions. And of course, the tracer particle feels the spring, the potential, and some noise. And of course, the bath particle only interacts with the tracer particle via the spring. Okay. And of course, you see now there are a couple of open parameters, gamma, gamma B, kappa B. And to adjust those, we compared the solution of that coupled Langevin equation with the probability distribution, the experimentally measured probability distribution, and the mean square displacement. And this nails down these parameters. And you see here for the gamma, for the friction coefficient of the tracer particle, we found a value which is about 1/8 of that of the bath particle. So the bath particle, that's actually the reason why I have made the bath particle much larger, to indicate it has a much larger friction coefficient. And this, of course, also leads to the fact that the relaxation time of the colloidal particle is much smaller than that of the bath particle. And that's important now, because what it means is if the tracer particle is making a sudden motional change, the bath particle cannot immediately follow, which simply means that at short time scales, the bath particle is not in equilibrium. Okay, and that is crucial for what I will show you now in the following. Well, before I do that, let me just show you that this, once we have fixed the open parameters, this model is in perfect agreement with our data. In fact, the orange line was already the result of the numerical model. And this also applies here to the delta U dependence of the timescales and of the amplitudes. I'm always a fan of having a simple argument for that. And I mean, you might say, well, okay, I believe this Langevin equation, but the question is there a simple argument we can understand why we have two timescales? And this is what I try to do here. Let's assume we have the tracer particle to be equilibrated, or let's say just by chance, it sits very long in the left potential well, so long that the tracer but also the bath particle are fully equilibrated. Now, by a spontaneous fluctuation event, this tracer particle tries to overcome the barrier, and because the friction of the bath particle is much larger than that of the tracer particle, you see this leads to a loading of the spring, which means that the particle is doing its motion. There's a lot of elastic energy stored in the background, which will very likely make the particle pulled back even before it's able to relax down. And this explains why we have here a short time scale, but it also nicely explains why this time scale, this short time scale here, is rather independent of the potential barrier, because the particle hardly will fall down and relax on the other side. If, however, the particle falls down, and there's also a finite chance for that, then of course this is a longer process, so then also the bath particle can relax. And if now in such a situation, the particle has to overcome the barrier, there is no elastic energy stored in the system, and the only energy source are the fluctuations of the thermal bath, KBT, which then leads to the longer waiting time and also rationalizes why we then recover the Kramer's results. So that's at least a hand-waving argument to understand that. Now, one consequence, of course, if you have a system with memory, is that you have a time-dependent effective potential. So if you have a Markovian system, the force, I just have to close a door here. There's some construction going on outside. Sorry for that. If you have a Markovian system, the force is simply obtained by the probability distribution that a particle which was at time t positioned at position x is doing a displacement over L within the time delta t. Then you multiplied it by L over delta t, integrate it, and if you then multiply a friction coefficient, this gives you the force, and from that you obtain the effective potential. In a non-Markovian system, however, you also have to know where the particle has been before time equals 0, so where it has been at time minus t. And this then leads to a time-dependent effective potential. And this is now shown here for the initial condition that the particle at time minus t was positioned in the left potential well. And what you now very nicely see, and this is in a perfect confirmation of this deposition of elastic energy, I was showing you just on the cartoon on the side before, or you also see here once more, at short times that if you ask yourself if the particle has been at minus 1 second in that well, what's then the probability distribution? And you see this becomes strongly asymmetric, because if the particle moves to the right, this means you have a distorted potential, because now also the elastic energy will affect this time-dependent effective potential. And what's very interesting is that even after 30 seconds, we still see an asymmetry, which means you need a lot of hopping events until this initial condition and the initial memory has been completely decayed away. That's also seen here in that inset, which plots the spatial correlation of the bath particle and the tracer particle, and you see only after about 100 seconds it decays. One immediate consequence of this idea is that we should be able to suppress short waiting times. And this is what is shown here. Let's assume we prepare the system in such a situation. We first have a single potential well, a very deep potential well, where we localize the particle, and we localize it there for 100 seconds, for a relatively large time. So everything, the particle and also the bath particle, is in full equilibrium. If we now suddenly switch to a double well potential, then of course at some point the particle will do a jump, and we now measure the waiting times, the distribution of the waiting times of the first jump, which starts from a fully equilibrated state, right? And we also measured the probability distribution of the second jump, where the bath particle is not necessarily in equilibrium, right? And this is shown here. This is actually the integrated waiting time distribution as a function of the upper threshold. And you clearly see this first jump here, the short times of the waiting times are completely missing. They are completely absent, and they only occur in the second jump. So this simply means starting from, I think that's a very nice confirmation of this simple idea I showed you here, starting from an equilibrated, a fully equilibrated system, we have only long waiting times in the system. Okay. Now, so everything was in equilibrium. So the only effect was the memory, which was important to describe our results. But of course, we can also change our protocol to go away from equilibrium. And actually, this goes back to all the data to all the experiments we did together with a former postdoc of mine, Ruben Gomez Solano, and we applied a similar protocol. We also were confining the particle in a trap, and then we were moving the trap with a constant velocity over relatively large distances. Then we were turning off the trap, and then, of course, the particle recoils. Okay, that is of course not that nice. I couldn't animate it better in PowerPoint. There's of course also a lot of fluctuations, and this is exactly how it looks in the experiment. This is the shearing. This is the recoil. It looks a little bit strange because in the experiment we are not moving the particle with an optical trap, but we keep the particle at the same position and move the sample underneath, right? So that leads while doing the shearing, because the camera is fixed relative to the optical tweezer, which is static. During the shearing, the particle looks rather static, but in the recoil, then the particle is released from the trap, and you clearly see here this recoil opposite to the initial motion of the stage. Now, if we now measure here the trajectories, this is what you see here in this pale colored curves. They show here a similar behavior, right? And if we do the mean value of that, this leads then to these open circles. And in fact, this can be very nicely described again by a double exponential. However, this is now not, this is very different. This has to be distinguished from the double exponential we have seen before. This was a probability distribution. Here we are really talking about the mean trajectory during the recoil. And double exponential, which has been also observed by Ruben Gomez Solano a couple of years ago for very, very different systems. However, we were never able to explain, to give a microscopic explanation of that.
It's like 5 minutes from here to...
That's perfect. That's perfect. Thank you very much. Okay, and the question is, how do we understand that? Well, I think it's pretty obvious that having a single bath particle, that's of course the first thing we tried out to apply the same model as before. This, however, would only lead to a single exponential recoil curve. What you have to do, formally what you have to do is to add another bath particle. This is what you see here. This is now our colloidal particle, which has, again, its friction gamma. And now we have to add two bath particles, which are connected via harmonic springs with different spring constants, and which have different friction coefficients. And you might say, well, that's a very naive way. That's a very naive model to describe the properties of a viscoelastic bath. But this is what I want to show you here, and this is then my last slide. It seems to explain very nicely what we see. For example, here I show you the two amplitudes, the short and the large decay in the mean trajectory as a function of the shearing velocity. And you see they increase linearly, and this is exactly what you see here with the solid line. This is exactly what's predicted within such a model. Again, you also see that the time constants are constant, so this is also an outcome of that. If you change the protocol, if you keep the shear velocity constant here, for example, 3 micrometer per second, but you change the shearing time, then of course the amplitudes will go into saturation, because at some point here the springs are fully loaded. Again, this is in very good agreement, and we also have other protocols, and we find a lot of evidence that such a simple bath particle model seems to be able to describe this complex behavior. Okay, so that brings me already to my summary. What I have shown you, I've shown you two types of experiments. One's equilibrium experiments, the thermally assisted activated hopping process of a colloidal particles over a potential barrier, where we have seen that we have two time scales. We have one much faster time, which might be also relevant might be to understand dynamics in biological systems, which often happen to take place in viscoelastic fluids. And in case of these non-equilibrium experiments, we also find two time scales, but now in a different quantity, the mean recoil dynamics, and they are now described by a two-bath particle model. You can ask why two bath particle models, why two time scales? Well, what we believe, there might be a resemblance to glasses where you also have an alpha and a beta relaxation time. Might be that's the deeper reason to that question. Okay, once more, thanks to Kartika, Felix, Juliana, Luis, and Matthias, and also thank you for your attention.
Okay, thank you very much. So I think we have a lot of questions, but we do not have so much time. So let us just go ahead and let me invite everybody for questions.
Shall I leave my screen shared?
Not, you can leave it, I think, yeah. So what questions? Maybe there is also something. I check YouTube, actually. Is somebody checking YouTube?
Yeah, we are checking YouTube.
Is there any question there or on the chat or wherever?
No, but somebody has raised a hand.
Who is that? I don't know. Ah, Satyaki, please.
Yeah. So, sir, am I audible?
Yes.
Yes. Actually, if there exists a number of barriers, then is there the time scale? There exist only two time scale, then, or there may have more time scales.
That's a good question. Of course, you might. I mean, of course, adding more parameters made the fits work better and better. On the other hand, what I find very convincing, you see, the two time scales are not depending on the delta U. So I think we have a lot of evidence to believe that there are exactly the two time scales, right? And as I tried to rationalize that. Obviously, that's a question we are asking ourselves. But two time scales is, I mean, from glasses we know that these complex networks, you have caging effects, and a similar thing might also happen in such viscoelastic fluids.
Okay.
Okay.
By the way, did you experiment at different temperatures as well, at the various temperatures?
We have not varied the temperature, but what we want to do, I mean, we have varied the concentration. That's actually has a much stronger impact on the material properties. And I mean, for example, this double exponential recoil has been also confirmed with completely different viscoelastic systems, lambda DNA, semi-dilute polymers. So it's a truly generic effect. Yeah.
Okay. But if I look at the theoretical model, if I recall the equations, you are modeling basically with let me call it a two-dimensional Markov model, where you could apply in principle Kramer reaction rate theory to a two-dimensional Markov model, except that here the question of passing the barrier is a kind of geometrically unusual one, because in this two-dimensional landscape, it's like looking at, like a one-dimensional direction. But if you somehow make abstraction of that, you would expect that there could be a second time scale, not so much in the exponential, but in the prefactor, in the Arrhenius factor. Kinetics, which is depending on temperature in a particular way, and has itself picked up another geometric feature. I mean, in two dimension and higher dimensions, these Arrhenius factors, they can become quite complex.
Yeah.
I think so. I was wondering whether that is at least theoretically also an option, is not to work with like two Kramer's rates with different scales, but like with the usual Kramer's, but the complication to be put in.
Yeah. I mean, of course, I mean, certainly one can rescue Kramers, right? That's, I think, what you suggest somehow. On the other hand, what we tried to link it a little bit more also to the microscopic properties. And that is actually, because see, at the end of the day, we suggest to use that type of experiments to learn something about the properties of the systems. And that's the reason why we found such a microscopic description with a bath particle with a spring. You might interpret that then in a local, the elasticity of a mesh or something like that. That's why we found it more appropriate. But I fully agree with you. Formally, this can be certainly, if you tweak the temp frequency a little bit, I'm absolutely sure you can recover that. Yeah.
It's a question of Abhishek, please.
Yeah. So, and sometimes I've seen like people modeling complex fluids using this other model. I mean, where you have a like resistor and a viscous element in parallel, right? So is that also
the Jeffreys model, for example, right?
Right. Yeah. So is that, I mean, something also easy to, one can do an experiment and what would, one see also these two time scales there?
Sorry, I didn't get what experiment you are suggesting?
So I'm saying like some fluids, like instead of the Maxwell model, you have this other model like Kelvin White model, I think, where
I see.
like resistor and in parallel, right? So is it possible to do, I mean, similar experiment in such a fluid and you'd observe something different?
Yeah, I mean, actually this Maxwell or Jeffreys model is, at least for soft matter systems, that is a good description, and I'm aware of Kelvin Folk model. That's right. Everything depends a little bit on the forces, right? I mean, if you have a viscoelastic solid, if it becomes very elastic, right, then of course the forces to shear a particle through such a system might be very large, and you might not want to use optical tweezers. But I mean, I would say in principle, to do such recoil experiments, right? For example, this should be also possible in other systems. You could use magnetic particles when you apply much stronger driving forces, for example. Yeah. I think it's not limited to our system.
It's exciting that already a two-particle bath model can get both for Kramer's reaction rate and for the non-equilibrium experiment such a good agreement. It's certainly remarkable already. Other questions? I think we have to move on, unfortunately.
Yeah, thank you very much.
Questions. So thank you very much, Professor Behinger. I think Anupam, are you the next and ready?
Yes. Can you hear me?
Hearing is fine. Maybe sharing your screen would also be good.
That is, yeah, I have done that too now.
Okay, so organizers, is it okay to continue?
Yeah, it is okay.
So the sharing is okay now?
Yes, it's perfect. Thank you. So next talk is by Anupam Kundu, where the title speaks about active motion at microscopic scales. Please.
Okay, thanks, Chris. And I'd like to also thank the organizers for inviting me to present some of our results. So in this talk, I'll talk about a collection of some recent results that we have obtained on active particles at individual scale. And I apologize that these results are mainly kind of informative in this talk. I'll not be able to provide much details. Okay, so let me start with Brownian particle. So this motion, it's very common, we all know. So in one dimension, it is described by this simple stochastic differential equation. X is the position of the particle, and this is external force, and also driven by thermal noise, which is characterized by wide Gaussian noise with these statistical properties. And this is a typical trajectory of a Brownian particle. So this motion is quite widely used in various phenomena as a basic description, starting from diffusion polymers. Queuing process also has applications in medical imaging, in finance, So it has a lot of applications, many more applications. But there are phenomena for which this motion, this description, you cannot use this description. For example, bacterial motion, chemotaxis, motion of granular particle in second granular matter. There are phenomena like walking of birds, swimming of fishes, where the Brownian motion type description is not very useful, because the individual constituents of this kind of system, substances or the agents at the local scale consume energy from surroundings and transmute it into systematic motion, and actually violate detailed balance. So such a kind of motions are called active particle motion. And when you have many such particles together, a collection of such particles, they show exhibit interesting phenomena like motility-induced phase separation, clustering, and also phenomena, if you put them in confinement, the phenomena like absence of equation of state, which means that we cannot write pressure in terms of other macroscopic variables of the system. But at the individual level also, they exhibit the interesting features like interesting large dimension properties, Boltzmann steady-state distribution in confinement, accumulation of the boundaries. Also, the shapes of the steady-state distribution are, you find different shapes on the crossover among these different shapes, different persistent properties, some universal features, etc. In our research group, we have mainly focused on, in the last few years, we mainly focused on these two questions. So how different are they from Brownian dynamics, and try to understand the effect of activity on some many particle phenomena, and I'll talk about those. So in the first part, I'll talk about this first part, how different are they from Brownian dynamics, and we try to understand this question by investigating specific questions, and out of those I have decided to present few of them, few of the results. And in the second part, I'll talk about some results on many particle phenomena. So there are actually many several models for describing active particle dynamics, and out of them, these three models are quite well known and widely used. Run and tumble particle is okay. Run and tumble particle, active Brownian particle dynamics, and active Ornstein-Uhlenbeck particle dynamics. And for in all three models, you have is written in as ddt of the position equal to, there is some the external force if you have, and sometimes you can have thermal noise. But one extra drive that is there is coming from some internal fluctuations of an internal degrees of freedom, which is called velocity commonly. So in the RTP case, it's in one dimension, it is described by some telegraphic noise. For an ABP, this comes from some internal degrees of freedom, which actually performs a rotational diffusion. For AOUP, you can think of also this as a velocity, which also gets originated from some internal degrees of freedom performing Ornstein-Uhlenbeck process. And in this case, the dynamics is like for the RTP case, the dynamics is the particle actually moves for some time in a straight line, and then tumbles and chooses a direction randomly, and then again moves for some time in that direction in a straight line, and again changes chooses a new direction and moves like that. Okay, so these are the kind of widely used models, and I'll present results in different contexts using these different models. Okay, so let me start with the first part. So we start with the simple problem where we have only one run and tumble particle on a line, and where in one dimension it is described by telegraphic noise, which takes values +1 or -1, and it stays in one value for some time, which is chosen from exponential distribution, and then change the value from +1 to -1 or -1 to +1, and then again stays there for some time, which is chosen from exponential distribution. So that's how this noise works. And the simplest question that we can ask is that what is the probability density of finding the particular position x at time t? And this question has been studied in various contexts, or in the slightly variants of this model, in different other models, which are slight variants of this model. And this question has been studied, and there are a lot of studies. So the main results that one finds is that at short time one observes that the effect of the activity is there in PXT. in the distribution. But at large time, the typical part of the distribution is kind of same as an ordinary Brownian particle as expected. But at last time, the difference with the Brownian particle is observed at the large deviation tail. Another interesting quantity question is the survival probability, where you start the particle at some position in presence of an observing boundary and ask what is the probability that it survives, it does not reach the observing boundary till time t, and at last times this survival probability decays as 1 over square root t, as same as Brownian particle. However, the p factor, the x dependence of the p factor is different for active particle. But the dramatic effect that you find is when you put this particle in a confinement. So when you put the non-thermal particle or the active particle in a confinement, it reaches a steady state, but the steady state is not equilibrium; it's non-equilibrium. That means, unlike Brownian particle, distribution doesn't have Boltzmann-Gibbs form. So suppose if it is a harmonic potential, then this, for a Brownian particle, you will find that this is the distribution of the position, such that the peak of the distribution will be at the center of the trap. But for a run and tumble particle, you find this kind of distribution, where first of all, the distribution is finite range, it's finitely supported, and you have weights which are larger at the edges than the middle, which means that there are at the boundaries. Such accumulation is observed in experiments, in various experiments. So this is an experiment in 2 dimension where they have looked at the motion of microshimers in between 2 plates, and they also have observed the accumulation at the boundaries. This experiment deals with Janus particles trapped by some acoustic tweezer, and they also looked at the distribution, the density of the particles, and they actually have seen different types of distributions depending on the strength of the confinement. The third experiment, this looks at different dynamical regimes of active particle, where they have considered the motion of a Higgs-Bark nano in a parabolic moving on a parabolic plate, and they also have observed accumulation at the boundaries. So of course, all these experiments are done in higher dimension, in 2 dimension, but it's good to kind of get an analytical computation or theoretical computation for such behavior, accumulation behavior, or the steady state distribution. But analytical computations are simpler in 1 dimension. So we look at the same problem where you have a random particle in some confining potentials V of x, and you try to find out the steady state, and it turns out that for an arbitrary V of x, there is an explicit formula for this distribution. And I should mention that this problem was actually studied in different contexts, in the context of colored noise, or in the context of persistent random walks earlier, and this formula was already existing, but we also have derived recently in a different way. But the implications of this formula were unexplored, and we tried to unexplore various features from this formula, and for that we had focused on this type of confining potential, which is controlled by these 2 parameters alpha and p. And the important features that we have, most important features that we have observed is that this distribution is finitely supported, and the second thing is that it actually exhibits different. It exhibits interesting safe transition on the alpha p plane. This is alpha and this is p, and you kind of find distributions of this type where you have accumulation at the edges. And also you find distributions of this type where you do not have accumulation at the edges, and this type of distributions are called a kind of passive type distributions, and this type of distributions are called active type distributions. And you see there is a crossover line, we can find this crossover line. Also we have another reason where you kind of find a collapse distribution also, but I will not be able to go into the details of those crossovers. So this is a slide in which I describe that we have also studied active Brownian particle in 2-dimensional harmonic trap, and where we again aim to find a distribution of the position of the particle, active Brownian particle in the steady state. So you have an active Brownian particle in a 2-dimensional harmonic trap, and this is the equation of motion. This is the force coming from the harmonic trap. This is the thermal noise that is present there, and this is the active noise that comes from the orientation degrees of freedom which is performing a rotational diffusion. Now, I would like to remind that once again that if you have a Brownian particle instead of active particle, that means you do not have this term, then you would find that the radial distribution would be like this. And the distribution in 2D would be like this kind of distribution, which is like Maxwell-Boltzmann distribution. However, for active Brownian particle, we do not see like distribution like this. So here I'd like to mention that in the steady state, this phi and theta coordinate actually appears always in this combination. So this distribution is actually a two variable distribution, R and chi. And we find this distribution explicitly by solving this Fokker-Planck equation explicitly, and we find that this solution is expressed in the power series of lambda. Lambda is a Peclet number which indicates the relative importance of active motion compared to diffusion. And also we have found these functions explicitly, these polynomials explicitly, how these coefficients are obtained from the Jacobson relations. And you see that this distribution is actually characterized by these two parameters, lambda and beta. Beta represents the ratio of the relaxation time scale and the activity persistent time scale. So these are the kind of typical distributions at different values of lambda. This is radial distribution, and this is azimuthal angle distribution, or the chi distribution at a given value of r. Now, these distributions are consistent with previous results. This is a theoretical result. They also got similar distribution, but using some approximate methods, and they found that when you change the Peclet number, you go from a passive-like distribution to active-like distribution, where the peak of the distribution is away from the center. And we also see that. And this experiment I have already talked about. Here also in the experiment they've seen this kind of distribution. Here you have a peak at the center of the trap in weak confinement, and if you increase the confinement, then the peak of the distribution shifts away from the center of the trap. Now so these are actually you see this kind of crossovers are in these papers are obtained using some particular tuning parameters. But in from our study, we find that actually in the full beta and lambda plane, you can find the full kind of a diagram, phase diagram, or let's say not call it phase diagram. So diagram in which you have region of passive-like distributions, and you have regions of active-like distribution, which looks like the peak is actually away from the center. And you see that there is for a given lambda which is above some critical lambda, if you start and increase in beta, you see that you start from passive and you reach an active like state distribution, and then again you find a passive like distribution. So it's like a reentrant phase shape transition that we kind of predict from our study, which are not earlier observed in this experimental or theoretical studies. Also, we have an explicit formula for this crossover line. Okay, so now let me talk about some our results on some studies on path functionals, again which aim to understand this question. And we have studied different path functionals, but I particularly like these path functionals which are related to Einstein laws. So these are R maximum, residence time, and last passage time. So what are these functionals? So for a trajectory of given duration, R maximum is the time at which the trajectory reaches a maximum, and residence time is the time the trajectory spends on the positive side of the positive side, and last passage time is the time at which the worker actually crosses the origin for the last time. So this is the last passage time, and after this time it did not cross the origin. So for Brownian particle, Brownian motion, the distribution of all three quantities are same. It is given by this, and the cumulative probability is also same, obviously, and is given by the arc-sine function. And that's why these are called arc-sine laws, and these are first derived by Levy. So we asked what happens to these arc-sine laws for a run and tumble particle. And we found explicit forms for this distribution, and these distributions are expressed in terms of survival probability that a particle, the particle starting from zero origin did not return to zero in time t in one dimension. Of course, it turns out that it has been recently shown by Francisco Mori and Soto and others that this survival probability is actually universal in general dimension, and also for arbitrary velocity distribution, and which is an artifact of Spire-Anderson theorem. So coming back to this the Einstein laws, we find that this distribution for R the maximum and the residence time is same, whereas the distribution of the last passage time is slightly different. Although all these forms actually approach this form in the large T limit. So once again, at short time you see the effect of activity, but at large time you again find get back the downward motion result. Okay, so now in the last few minutes, let me talk about the our results on interacting particles. So here, the most there are many phenomena. The most common phenomena is the motility-induced phase separation, and which actually is due to the kind of feedback that some kind of feedback that one gets from the insight from Kiosk-Gunn theory. However, from a microscopic point of view, one might think that that must be an effective attractive attraction, and there are very less systematic. Very few systematic studies, microscopic studies, which tries to actually understand this emergent attractive interaction. And among these, I like this most the work by Martin Evans and his collaborators. So what they did, they actually looked at two run and tumble particle, which are actually performing some persistent random work on this periodic lattice, and they are doing moving with exclusion interaction. And they looked at the gap between these two particles, and they found that in the steady state, the gap has three parts. One jammed part where the two particles are stuck at the site, neighboring sites, and you have a bounded part which is exponentially decaying, and you have an extended part which is uniform. And they interpreted this distribution, the probability function, as an effective attraction. So we looked at the same problem, but on a continuous ring, but again, now in presence of a thermal noise. So we have these two run and tumble particle. We have this individual telegraphic noise, which are doing tumbling with rate gamma, and these are Brownian noise. And these forces represents that they are hardcore interactions. So these are typical trajectories of these two RTPs. And the corresponding trajectories when these activity noises are switched off. So these are the corresponding trajectories of the passive when they are made passive. And we see that for the RTPs, they actually tend to stay together for a longer period of time. And once again, we look at the distribution of the gap between these two particles, and in the steady state, and we find that again the distribution is actually has three parts, but now the jammed part becomes an exponentially decaying part with a different length scale. So you have two bounded part with two different length scales, and once again you can interpret that as a effective interaction. But interesting part that we see is that to the relaxation. Of course, here we find that the relaxation is exponential, but the relaxation time undergoes a crossover with the ring size. So there is a critical ring. So when the ring size is smaller than that critical length, the crossover is the relaxation is controlled by the tumbling rate. When the L length is larger than this critical length, then the tumbling is controlled by the effective diffusion of the model. And similar crossover is also observed in a single particle, steady state of a single particle in confinement. Here I was looking at the gap between two particles, but similar crossover is also observed for the steady state of a single particle in confinement.
Anupam, it's like 5 minutes.
Yeah, okay, I'll finish. So, so in the last few minutes, let me talk about the last part, which is some universal features in single file problem. So here we look at many active particles, and they are moving in one dimension, and they are interacting, and you have thermal noise and you have active noise, and these active noise has different forms for different models. And we look at how does the mean square displacement grow with time. So first we look at the situation when there is no interaction, and we find that you can find out the mean square displacement for all three models. But it turns out that if you look at, if you identify the common velocity scale and the persistence time scale, then all three expressions can be written in this common form. So which is a kind of universal feature across active particle models. Question is, does this universality also persist if you have interaction? And we consider this kind of interaction. So these are the trajectories when you have interactions, and these are active particle trajectories. So they try to cluster together, and we are interested in the fluctuation mean square displacement of the middle particle, which is our tag particle. So we measure them numerically for different models at different density, velocity, and persistent times. And for all of them, we find that it is t square at small time and crosses over to square root t for all three models. But interesting fact is that if we appropriately scale by some factor, which depends on rho, velocity, and persistence, then the time is measured in the persistent time, then all curves actually collapse. So you have a scaling function. Array represents these models. But interesting fact is that this function is same for all of them. That means all data actually collapse into a single curve. So it means that the universality still persists when you have interaction. Now we wanted to ask how does it cross over? Is it controlled by activity? And it was difficult to do perform any analytical calculation for this particular interaction. So we looked at a harmonic chain problem where we considered a particular uniform initial condition where the particles actually start their initial position, and look at the tag particle, and each particle is driven by some activity. So in such setting, actually MSD is basically same as variance, and we looked at the variance. In this problem, there are three time scales. One is this interaction time scale, then activity time scale, and also a time scale due to the infinite range, finiteness of the ring. And we look at the problem in this range, and we find that at a time which is very, very smaller than the interaction time scale, it is t square. When it is larger than tau a and this, it is square root t that we have already observed. And in between, you see that this means the displacement or the variance actually goes to the power a, where a takes different values for different models. And not only that, we actually also looked at found the crossover from this behavior to this behavior. And this is the crossover function that we have obtained, which is also validated by simulation. So in conclusion, I say that we have investigated mainly these two questions by looking at different specific questions, and we find that at short times activity affects the dynamics, and at last times the activity has effects only at the large fluctuations. But in the steady state, activity has dramatic effects because it makes it a non-equilibrium, and the distributions are non-Boltzmann type. And the relaxation of the steady state also gets affected by the activity. And in the many particle regime, we find that hello.
It's okay.
Somebody says that I'm not audible. So
you're very audible, Anupam.
Oh, I just saw a popped up message in my screen. So sorry. So let me continue and finish. So within confined geometry, activity introduces effective interaction among active particles, and in single file problem, we find some universal features in the MSD. However, this universality is not present if we harmonize the interaction. Although those harmonization technique can predict some crossover from one growth regime to another growth regime. So these are the collaborators, and I would like to acknowledge the funding from SCRB, India, and SEPIPRA, and thank you for your attention.
Thank you very much, Anupam, for this review covering lots of topics. So we have time for a number of questions, but let me remind you, or let us be reminded also that after this session, there will also be these breakout rooms where speakers will be available for other discussion and questions. But for now, what are the most urgent questions for Anupam? Anybody wants to start? Yes. Shadra?
Yeah, Anupam, I have a very quick question to your last part where you showed this exponent A for intermediate time regime.
Yes.
So does it also depend on dimensionality, or these numbers are same in all dimension? Any idea? Or this calculation is for one dimension?
Yeah, the chain is in one dimension, but the particle motion could be into, for example, ABP, we have in two dimensions. So the fluctuations are in two dimensions. The chain is actually one-dimensional chain.
Okay. Motion is in two dimension, but the particles are located in one dimension.
Yeah, and RTP is in one dimension.
Okay.
Yeah, but we didn't look at a higher dimensional RTP problem.
Okay. Okay, thank you.
Okay, thank you.
There is another question, I think, in chat.
I don't see it.
Ayan, why don't you start? Ask yourself. Raise a hand and ask.
Should correspond to the no. It's I said that the T to the power A is the
What's the question?
A that we hello.
Yeah, you're answering a question, but I don't know which question.
No. In the chat, Ayan wrote a question in the chat.
Maybe Anupam, if you can read out the question also.
So, is there a regime in the tag particle study with Lennard-Jones potential where the universal scaling function doesn't work, which would correspond to the T power A in your harmonic chain? So, no, actually, this T power A is between T square and T per half, and here we see that it's actually here also it has this universality. So our harmonic chain does not describe particularly this curve, but it has this crossover. It qualitatively describes a crossover, that it has this feature, T square and square root T, and in between you have a T power law behavior, but it doesn't describe this particular problem that we have studied with interaction. So harmonic is kind of a simplified version, right? You do not have particularly much interaction.
Okay.
So this does not describe this part.
Yeah. So the tagged particle is also active, right, Anupam?
Yeah, all of them are active.
Is it important?
For the square root T behavior and T square behavior, it's not important. For T power A behavior, I'm not sure. I think you should have this T power A behavior, this behavior. I think it should be.
Maybe there is a question from Tripta Bhatia. How do you model the active noise separately from the thermal noise? Are there experiments published on these noise measurements? I mean,
there are experiments. So, for example, I would like to say that. So, first of all, these are the models of active noise that we have said. It actually you have to create the noise in such a way that it doesn't satisfy fluctuation distribution relation. So, for example, in this model, I forgot to mention. So, there are experiments in which actually they have done experiments in I think the granular particle, and you found out the position correlations and the fluctuations experimentally, and they described those data using this model, and that fits extremely nicely. So that describes those data. So that means there are experimental verifications of these models, and the active noise is described by theoretically in different models as this.
Okay, thank you very much. That's of course an interesting discussion also in what sense these noises are just colored noise as any other color noise, or whether there is a kind of more deeper physics derivation of these models. But I suggest we do that in the breakout rooms. I think it's now time to move on. So thank you again, Anupam, and let us turn to the next talk. Who I see Olivier is here. Hello, Olivier Rochaud.
Hello.
Hello. So maybe you can try to share your screen.
Yes. Okay. Okay, doesn't want. Let's try another time. Sélectionner fenêtre dans l'écran.
Doesn't work. You have to.
Doesn't want me to share.
You're able to share? Or?
No. Wait a minute. This is the one. Okay. Okay, I see. Okay. Where are you? Here. Okay. Okay, let's try once more. Sorry for that. Okay, here. Microsoft. Autorisé. It doesn't want me to share.
So can we help somehow on our side?
They ask me. Wait.
Are you presenting from Mac?
Yes.
Then you have to give a separate permission for screen recording or something.
Yeah, that's what I see. That's what I see. Ouvrir le lien. Ouvrir le lien. Okay, let's authorize this also.
Now he has left.
Maybe he will come back after security was cleared.
Back.
You're back, Olivier. Bonjour. But do you have permission now to share? Or?
Let me try again.
Okay, great.
Autorisé. Just a second. Okay, it's gonna work. I feel it's gonna work. Okay. So do you see something now?
Yes.
Yes, it's coming.
Something is coming. Okay. So what do you see?
We see a full screen. Now, if you minimize the browser and open the...
And now? So what do you see now?
Still the browser.
Why the browser?
Did you select one window or entire screen?
No, I selected the full screen. Okay, let me try to select only one window. Just a second. Okay, up. Okay, let's try this now. Only one window. This one. Okay, it should work now. So what does it give now?
Nothing yet. It's coming.
Oh, there it is.
Yes.
Okay.
So just make it full screen. Just make it full screen.
Okay, let's make it full screen. What about now?
Yes. Most important, can you change the slide?
Is it okay now?
If you can go to the second one as well, that would be great.
That's what I just did.
No, we only see the first slide now.
Let's try this way. What about this way? No?
I think that's the problem with sharing just the window.
Yeah, now it works.
Yeah.
Now it's working. Yeah.
So you have the second slide, right?
That's with the sheep.
Okay. So let's keep why active matter is interesting for physicists, because you are all there for that. So let's move to the outline. So
please.
So the outline will be in three parts. The first part is to say that walkers are also self-aligners, and I will say what I mean by this. And then I will describe you spontaneous flows in crystalline structure and selective and collective actuations emerging in linear elastic system. So before doing this, please forgive me for this mess, and let me thank you for the invitation, of course. Okay, so let's move peacefully. So I consider a typical walker, which are the X-bug. So these little things are toys that you can buy on Amazon, and the energy source is a battery, and they have a polarity that is designed in the shape of their legs. And so if you switch on the polarity, the engine, then you can see that this thing starts running everywhere. So they're a very good model for active matter. Okay, so how would you describe this? Well, you can use Newton's laws. So you have the accelerations that is proportional to the active force. Then there is some damping and, of course, the usual external forces. But then, well, in principle, because these particles have an angular degree of freedom in the plane, you should also write the Newton law for the torques and the momenta. And so you would, in principle, write that the rotation rate acceleration is proportional to the external torques. There would be some noise. There could be some damping. But you see my slide, but you don't see them the way I want. Okay, so wait. Okay, let's stop this. Oh my God. Okay, so I want you, do you still see my slides?
Yes, we see the hex box, we see the slide, yeah.
Okay, so I want you to look at this movie here, where I impose the motion and I look at the behavior of the X-bug. And you can see that the X-bugs align on the motion that I impose. So it means that in the equation above, you can forget the first equation because I impose the displacement, and we can concentrate on the second one. And you see that there must be a torque that couples the second equation to the displacement of the particle. So that's what I call self-alignment. It's a very important point. So it's the fact that when
we didn't see the movie, just to make sure we didn't see the movie.
Oh my God!
But that's okay.
You didn't see the movie?
No, it flashed on like a minute ago, but then we don't see anything from the movie.
Okay, and this way?
This we see.
Okay, you see, I impose the displacement, and you can see the little X-bug in black aligning on the displacement that I impose.
I see, okay.
Okay, okay, so this is to say that the second equation, which describes the dynamics of the angle, must contain a term that couples it to the first one. So the simplest way to do this is to have a torque, an active torque, which is the fact that the orientation of the particles align on its displacement. This is a term that is always absent in most of the models that, for example, we just heard about. And it's a very important one, as we shall see in the following. Okay, so it happens that this is actually present for all walkers. We have a system of walking disc. Okay, let me move to this slide. We have a system of walking discs. These walking discs are just little metallic discs with two different legs that we shake from the bottom. And because of the anisotropy of the disc, of the legs, these things exhibit also a directed random walk. So this is a priori also a very good example of a realization of active Brownian particle. But again, you will see on the movie below that this little disc is going to align if I impose it some motion. So you can see there is a very small black dot on the disc in the movie below. And now I will shake it. It will start moving and also fluctuating in orientation. But now I will push it. And when I push it, you can see that again, the little black dot is always now at the back of the motion. So it has a line on its own orientation. So the message here is that if you are walking, because essentially your design is left-right symmetric with respect to the polarity that has been engineered in the particle, when your displacement is not aligned with this axis, you naturally experience some torque. And this torque realigns you in the direction of your motion. Okay, as a result of this, when we studied these systems, just putting this disc on a plate and shaking them, we could observe collective motions that I can illustrate with this movie, where this is an experiment and we track all the discs and their orientation. And you can see that although there are discs, so there is no steric alignment, this self-alignment itself effectively translates into alignments between the particles. And because of this, there is some kind of collective motion. You can actually simulate these equations in periodic boundary conditions, and then it's even clearer that you really have a large-scale connective motion, macroscopic order. You can compute all the phase diagram, perform very large simulations, and you essentially obtain the Witschek-like scenario for the transition to collective motion. So the message here is, despite the fact that these particles are circular, self-propelled particles, they should almost be the ideal realization of active Brownian particles or active Ornstein-Uhlenbeck one. At the end of the day, because of this self-alignment of the polarity towards the displacement, you cannot avoid an effective alignment between the particles. Okay, so this is all about collective motion. And what I want to discuss today is more what happens. Of course, the slides are going to be completely messed up, but okay, let's do it this way. Let's make the... is what happens if you really move to solids. So if you have disk, something you can always do is increase a lot the packing fraction to a point where you crystallize. This will happen. If you do this with passive disks, so if you do this with passive disk and you start from a perfect hexagon where so the arena is now an hexagonal shape, and you exactly pack the number of disks so that you are at close packing. So here, when the number of disks is 1,141, you have a perfect close packing of disk. And even when you shake, essentially, you almost have no vibrations. Okay, then you remove a few disks. And when you do this, you will have geometric frustrations. And so you will see defects, and this defect will slightly move. And then you remove a few more disks. You have other kinds of defects that appear. You can see that they can move a little bit more. And then if you even reduce more disks, you will recover a crystal because you are still very far above the crystallization transition limit in 2 dimensions. And you don't have any more frustrations because you removed exactly 1 layer of disk. So there is no more geometrical frustration, and you can have a crystal, just it's a little bit less dense, and it vibrates. And if you look at the pair correlation function, you can see this crystal forming, and you can see the pair correlation function here, which are plotted at different packing fractions, these 4 packing fractions, and you can see that the peaks are very sharp, and also that they move slightly to the left, that is, you are denser when you increase the packing fraction. That's the passive physics. If you do the same thing, with active one, it's completely different. Of course, when it's at close packing, nothing moves, nothing can happen. But then when you remove a few disks, again, you have defects. There is not much difference. But the difference is when you remove more of the disk, instead of going back to a crystal, you go to something with many more defects, and things are moving much more. And actually, you progressively melt your crystal. Still, what is interesting is that when you look at the pair correlation function, you still have peaks, and these peaks are always at the close packing position. That is, the regions that remain crystalline are actually close pack to leave place for the others to move. Now, if you look at a movie of what is going on, it's even more surprising. So here is a picture. You can see where you are crystalline, you are close packed, and the system has somehow concentrated the free volume in a region where things are going to move. Okay, so let's see how these things move. You may think that only the regions where there is room is going to move. Actually not. Everything is moving, and you actually have a collective motion of the close packed regions around the boundaries of this arena. In the center, it's disordered. But despite the very, very high density, the system still self-organizes into this collective motion. Okay, you can actually check this numerically. And when you perform the simulation, I skip a few parts not to be late. If you perform the simulations in the noiseless limit or in very, very, very low noise, then what you get is this. That is, you have a perfect crystal, very, very close, nearby to close packing. The packing fraction here must be something like 0.895. That is performing this perfectly periodic motion with these defects propagating from the corners that ensure all the shear that you need to allow for the rotation. Now, I want to conclude on this part with the fact that if you increase the system size, you don't kill this effect. On the contrary, you enforce it. That is, when here the simulation was with 1,000 particles, but with 30,000 particles, the pair correlation function is even more sharp, and your rotation velocity on the side is actually increasing, and also the fraction of the system that rotates is also increasing. So you have a bona fide flowing crystalline phase when you pack very closely these self-propelled, self-aligning disks. Okay. So this has motivated us to ask the question, okay, but now if we prevent them from rotating, that is, if I really want to consider an active solids, how should I do this? Because here it's still flowing, so I don't even know exactly what names I should give to this. So, So if I want to do this, essentially I should have my active particles, which are free to move, but I should embed them in some way with a reference configuration. How can I do that? Well, the idea is to take the active particles, to put them at the nodes of an elastic lattice, where the translational degrees of freedoms now are They can only vibrate, and the rotational degrees of freedoms are still free to rotate. So what will happen? Now, these little red arrows now are exerting forces, of course, on the elastic structure, and this will generate some kind of elastic strain. Now, this elastic strain is a tensor, and the tensor lives in the same space as the vector field of the forces. And so it's very likely that the tensor will act on the orientation of this force and will rotate them in some way. We call this elastoactive feedback, and I think it's almost impossible to avoid it. So can we realize it experimentally? So we did that by using, again, these little toys. And I recall you, they also have this self-alignment property. So we essentially put them in a plastic annulus, and all these annulus are connected by springs. And so you can realize really experimentally what the idea, these gedanked experiments that I had in mind. Now, these little active things will, of course, pull on the springs. This will define an elongation length, LE. But also, when the others are pulling on it, it will have to reorient on the motion that the others imposed it. And so there will be a reorientation length that is the distance on which you must displace these objects for it to reorient on the displacement that you imposed. And so a priori, there is a good control parameter, which is the ratio of these two lengths. Okay, so let's look at the kind of dynamics that we observe. So we have all these guys that are coupled together. Well, first, if you don't attach them, then what you get is actually the fact that through the elastic interactions, you mediate an effective alignment, which is another way of exploiting this self-alignment property, and the whole structure translates. Now, if you don't break the symmetry by having a guy in the center, you can also observe solid body rotation. And somewhat this is expected because these things has three actually trivial zero modes, which are the true translational mode and the rotation one. And because you inject energy in this system, well, of course, the energy will go in the zero modes. And so what we see is quite expected. Although still, I find it quite amazing. But so now let's pin the boundaries. So I pin the boundaries of my elastic structure. So now there is no more zero modes. It's a stable elastic structure. And I switch on the engines. And then what you can see is that, of course, all the little guys, they are pulling and pushing in all directions. And you have some kind of a disordered motion of the nodes that are free to move. But now let's take a little bit less stiff springs. That is, we increase this control parameter. And what you observe now is, again, a collective behavior of a new kind. You have some kind of synchronized oscillations of the nodes of the crystal, which is something completely new that I now want to discuss. Okay, so this is really because of this. Yes, this is really because of this self-alignment that are coupled through this elastic, through elasticity. The first thing that we did was to check that if you perform simulations of the equation in the overdamped limit and in the harmonic approximation, then you see the same thing. For exactly the same size, you see the same thing. So already there is a message that is, it's not the elastic nonlinearities, either geometric or in the springs, that are responsible for that. It's really the self-alignment terms that is responsible for this interesting physics. You can check if this is present in large system, and it is. You can see here that the whole system is rotating. Not the whole, actually. There is a boundary. I will come back to that. But a significant fraction of the system is, again, collectively actuated. So you have a solid dynamical chiral phase with spontaneously broken parity symmetry that emerges in this system. Okay, so the main message about these dynamics is that there is something completely not usual. That is, you can change the geometry of your lattice, of course. You can play with different kind of lattices. And what is amazing is that, for example, here on the Kagome lattice, although, again, there is no zero mode, what you can see is that, well, in all cases, first, the dynamics condensates on a few modes, which are the blue modes here. So here, I've decomposed the dynamics on the elastic modes of the structure. And in blue, you can see what are the modes that are predominantly actuated. And what you see is that for the Kagome, First, always these modes comes by pairs. Second, for the Kagome, it's not the lowest energy modes. So the geometry of the modes matter a lot in the selection of the dynamics. So there is a non-trivial modal selection that is rooted in this mode geometry and that we would like to understand. A second point about this physics is that the transition from the disordered state to the collectively actuated one, when you increase this control parameter, is discontinuous. A little bit like for the collective motion, what you have is when you so at very high value of the control parameter, you have a fully collectively actuated regime. And when you decrease the value of the control parameter, you see that you have a region coming from the side where the system freezes. And then at some point, you have a coexistence between, progressively, you have a coexistence, a spatial coexistence between this frozen regime and the collectively actuated one. And simultaneously, the rotation frequency of these oscillations decreases. And at some point, it reaches zero continuously, so that this region here in the center will stop homogeneously at some value of the control parameter. Okay. So how can we understand all that? There's one thing that we can do, although it's very, let's say, rough, is to look at a continuum description of all this. So you consider macroscopic fields, you average the equations on a small volume, so somehow you coarse grain the dynamics. And the first equation is purely linear. So this one will coarse grain very easily. You will just find essentially the same equation, except that the elasticity is now replaced by continuum elasticity. And then the polarities, which were unit vectors, becomes a magnetization or a macroscopic polarity, call it the way you like. And you will recover a self-alignment term, so that is the magnetization aligns on the displacement. But because if you inject this here, you see that the magnetization cannot, I mean, the cross product with the magnetization will be zero. So essentially you align on the elastic force. And then there is a term that emerge from the cross graining, which saturates the value of the magnetization. And if you look at the mean field solutions for these equations, what you find is that, what you find is that there is one solution with zero magnetization, that is this one in black, that is stable up to some value of the control parameter, and then becomes unstable. And there is one solution for the fully magnetized system, m equal 1, which is also an oscillating solution with a rotating frequency omega that depends on the control parameter. So although omega decreases continuously to zero, this transition is strongly discontinuous because the two branches of solutions are completely disconnected in phase space. One is a zero magnetization one, and the other one is a fully magnetized solution. So although despite the appearance of this diagram, the two solutions are completely disconnected, and there is a region of coexistence in parameter space. So that's what we learn from the mean field description. Okay, so what can
we have like 5 minutes or something?
Yeah, I could see that. Yes, I'm fine. So this is really the mean field level. So can we say something at the level a little bit more precise? So one thing that we can already look at is just simply the dynamics of one particle. So if you look at the dynamics of one particle, well, the first message is that you also have the same transition. So let me activate these movies. You cannot see all of them. Okay, so after a small transient, you will see that at the level of one particle, you have the same motion. So the oscillation itself is not a collective effect. What is collective is the synchronization. So then immediately you would think, okay, it's some kind of a Kuramoto synchronization of oscillators, but it's not. The reason is that already at the level of the one particle, the oscillations is not due to a Hopf bifurcation, not at all. There is no complex values in these problems, complex eigenvalues in this problem. Let me just try to show you this in 1 minute. So if you look at your equations controlling the dynamics of this particle, of this unique particle in the harmonic approximation, it's very simple. You have the active force, you have the harmonic trap that resists the active force. So if you look for a steady fixed point of this first equation, it's just the balance of force. The active force balances the elastic force. But as soon as this is true, the second equation is immediately because then U is aligned with N, the second equation is immediately satisfied, which means that all directions are all configurations where the particles point in one specific directions are static fixed point of the dynamics. So you have an infinite set of fixed points which are on a circle. So here this is a representation of the displacement X and Y. So you point in some direction and you are static and it's stable. Actually, it's marginally stable. And then what happens at the transition is that all these fixed points become simultaneously unstable, and you start moving along the manifold that was defined by these fixed points, except that now you rotate around it, but you start with an infinitely slow frequency, and then progressively the frequency will increase when you go away from threshold. So this is a very different kind of bifurcation from a Hopf bifurcation. The eigenvalues that separate the stable regime from the oscillating regime is a purely real eigenvalue. Okay, so unfortunately, when you consider n particles, the physics becomes really tricky in the sense that you have now all the possible configurations with all these orientations pointing in any directions that are stable, and unfortunately, they don't destabilize all at the same point. So it means that when you vary your control parameter, you will have all a regime where you have some fixed points that are stable, some fixed points that are unstable. When you become unstable, sometimes you move to a new stable fixed point, or sometimes you transit to the periodic solutions. And so it is very difficult to have a clear image of the phase space in this regime where we observe the spatial coexistence. Let me skip the details just by saying that there is one case when we can learn more, and this case is if you consider the one-dimensional system. So if you consider a linear chain, then you can compute exactly the periodic solution, and you can demonstrate that it is the only stable periodic solution, and then you still again have this coexistence region here that is the complicated region that would require more work to be described. Okay, I will conclude here with a summary of this physics. Oops. So you have generically you will have a nonlinear elastoactive feedback that promotes a collectively actuated chiral phase. The collective actuation is selective, and there is some kind of a selection principle that is not only lower energy of the modes. It's a mix of the fact that they need to be extended, they need to come by pairs, they should be locally orthogonal. So all this I didn't have time to really discuss, and we don't have a mathematical proof for that. This last part is yet something that we need to understand better. The transition is discontinuous, and it exhibits a spatial coexistence between the frozen and the chiral phases. Okay, so with this, I think active matter has made tremendous progress in the past 25 years studying liquids, and we just start considering really dense systems or really elastic systems, and it seems there is a place for a bunch of striking and interesting phenomena, and probably for understanding deeply these phenomena, the tools from more standard condensed matter will be of interest. So I would like to thank you all here, and if you are interested, there is this PhysRev letter about the flowering crystal of disk, which was the first part of the talk, and then for the collective actuation part, you can go and see this archive that is on the verge of being published in Nature Physics. Thank you very much, and sorry for the mess at the beginning.
Thank you very much for these fascinating phenomena. So we have certainly time for some questions, please. There are some chat or YouTube questions, I don't know. I mean, my general question, it's quite general, is that in what sense are these phenomena also similar, or reproducible, related to, the elastomagnetic effects? You can start from a Landau-Lifshitz, I think it's called Landau-Lifshitz-Gilbert or something equation, and couple it in a lattice, and you have to the Rashba mechanism and all that, and then I can imagine you have the usual spin-torque coupling and so on. So in what sense is this different for active systems?
So no, that's a very good question. So we actually even studied a liquid of spins where the spins were aligning on the velocities of the spins. And that was an Hamiltonian system. So there we were at equilibrium. So there is a difference. The difference is that, so although you observe also very interesting things in these systems, in these active liquids of spins, if I can call them this way, or more
Hamiltonian liquids of spins.
No, they are equilibrium liquids of spins with self-alignment. And so the point is that, so you have interesting effects that are sometimes similar, but you cannot escape constraint from equilibrium. So typically, in these systems of liquids of spins, you cannot escape, for instance, the momentum conservation. And the momentum in such a system of spins where the spins align with the velocity is not anymore just the mass times the velocity. It's the mass times the velocity plus the coupling constant between the spin and the velocity times the magnetization. So imagine you take a disordered system, the momentum is 0. Suddenly the system magnetized because you decrease the temperature. But because of the momentum conservation, the system will move in the direction opposite to the magnetization to keep the momentum 0. So equilibrium constraints will put a strong carcan on the physics that you can observe.
Okay, you can add magnetic fields, of course, and inhomogeneous magnetic fields.
Absolutely. And indeed, in this system here that I just discussed, you can think about adding an external field. A very simple way to do this, and we are just starting to study that, is you incline the plane on which you do the experiment. So now you have the gravity force that will pull everybody down, which means it will displace everybody down. So the guy will align on that. So you will be able to magnetize your system and see how it influences the collective actuation regime. So there are certainly the tools of the magnetic systems will be useful, but the physics will also be different.
Okay, thank you much. Again, there will be the breakout room later, but I think, is there a question on the chat here?
No, I don't see any.
Okay, not really. Okay, very well. Yeah, just one more question. I mean, you for somehow, because of the beginning, I was not following exactly well there, but there was the control parameter pi. Can you can you repeat where it enters somehow?
Yes. So this control parameter pi is here. So on one hand, the active force pull on the springs.
Okay.
So this creates an elongation length because you pull on the spring. Okay.
Okay, but is there like a persistence parameter here?
Yes, in some sense, yes. You can see it like this. Although it's really a length in the overdamped dynamics, it's really a length.
Related to time.
It's the length that you must displace the particle to reorient it. So you cannot. It's more or less. It's almost 1 over a persistent time. If you are very, very persistent, no, that's the same. If you are very, very persistent, you will need to displace the particle a lot to align it on the displacement.
Okay. So thank you once more, Olivier. Thank you very much. I think we need to go on with the schedule and to find Raul Marate, who is here to share the screen. Hi, Raul.
Hi.
So can you try to see if it works? Okay, there it is. Thank you very much. It was, yeah. Effective equilibrium of non-equilibrium, please.
Okay. Do you hear me?
Yes, we do hear you. Thank you.
Okay, so thank you very much for giving me this opportunity to present my not so recent work, and it might be a repetition for some of the attendees here. So sorry for that. So this work has been done with Victor, who is in Prague, and this was published in December 2020 and also selected as a spotlight in active engines to 2021. Though the title here says a kind of a general statement, but I will be focusing more on these active heat engines, which is a very popular topic among researchers now. So we know that in thermodynamics you have this Carnot or Stirling kind of heat engines, where there is a working substance, you take it in contact with a heat bath at higher temperature, and then equilibrate it, and then remove it and take it in contact with a heat bath at lower temperature. And if you do it in a particular fashion, then you can extract work, and then this will give you a famous Carnot or Stirling kind of an engine. Carnot, of course, is an idealization, and it's the maximum efficiency you can get in this sort of an engine, and it's given by the ratio of the cold and hot temperatures, 1 minus that ratio. But if you want to find out the efficiency at maximum power by doing this kind of a cycle in a finite time, then what you get is the Curzon-Hurlbon efficiency, and that is again a very elegant expression, which is just 1 minus square root of Tc by Th. Now, recently there have been a lot of studies where people actually study Brownian heat engines. So based on or motivated through this thermodynamic engines, you reduce the scales of the system to a single Brownian particle, or from macroscopic to microscopic dimensions, and a lot of them have been also realized experimentally. So usually this is kind of a comparison between what you have as passive versus active heat engines. I will explain what I mean by that. So passive engines are well known, and you may have something like isothermal flashing ratchets, where you flash these ratchets, and because of the asymmetry of this potential, the particle may move in shows a directed motion. Then there is a colloidal Stirling engine, where you perform a very similar kind of the protocol, where a particle is trapped inside a harmonic inside an optical trap, and you change the strength of this trap in a cyclic manner, mimicking basically the change of the volume in the usual PV diagram for the Carnot engine. You may also have what are known as active engines, where these bath where not only thermal fluctuations exist, but also some active fluctuations exist, maybe due to the presence of active particles, or like bacteria, which is basically done over here. So a similar kind of a Carnot or Stirling kind of an engine can be also achieved using this active particles, where a similar kind of cycle goes on, but you also have active particles which are inside this bath. So this is again the same example, where you do this for a single Brownian particle, and then you find some efficiency which is quite small as compared to the thermodynamic Lalage engines. There is another example of passive particles which was published by Martinez in 2016, where you actually do a Carnot protocol and find out these engines. Recently, from Professor Sood's group in ISC, they actually looked at an active particle heat engine, where basically you do a Stirling protocol, but the thermal as well as active fluctuations are present in the bath. So a typical example would look something like this. So you have some kind of a working substance, a ratchet, let's say in this case, and then there are these bacteria which are basically colliding with this asymmetric ratchet tooth, and trying to move it in one direction. And these are maybe called as what, so because the moment, this moves because of the collision of this bacteria with this asymmetric tooth, and you see that there is an unidirectional motion. Now, what we would like to see is that, suppose you have a very similar situation as in that movie, that you have a single particle which may be confined in a confining potential, need not be a harmonic, in general some mod x to the power n kind of a potential, and you have active particles as well as thermal fluctuations inside that bath. And when you have such a situation, why is it important to study this kind of thing? Because in general, if you can define an effective temperature, T effective, like this, then the heat currents which are present, due to the interaction of this bath and active particles with the with the working substance or the colloidal particle, can be termed as heat currents only when there exists an T effective. Okay, and in general, this T effective can be very, very different, or the effective temperature can be very different from the temperature of the thermal or the thermal temperature of the bath. Okay, so the idea is whether this is a completely non-equilibrium system and whether you can map it to an effective equilibrium system. And the question is, can we always do that? And can there always define an effective temperature in such situation? And this is what we want to study. So a general setting would be something like this, that you have a Hamiltonian which has a time dependent part, usually a spring constant or a trap that changes its strength time dependently, and it depends on the coordinates and the momentum of the particle. And h can be an arbitrary function of position and velocity in general, and kt is this externally controlled time dependent parameter. So the Hamiltonian may look something like this, where kt is this time dependent part, and x to the power n, where n goes from 2 to 4, is the confining potential in which you have put this working substance. So you can write down the Langevin equation in this fashion, and this f is nothing but your friction kernel. In general, this need not be delta correlated as you would usually do for a Gaussian white noise, but it may have some memory which is basically like this, and it can be an arbitrary function of t minus t prime. Only thing is that this eta is an additive noise, and we also assume that because the system is in non-equilibrium, as over here, because it consists of several non-equilibrium entities, what we do is that we do not assume that the fluctuation dissipation theorem, the general fluctuation dissipation theorem, is valid. So it's basically broken. Okay, and that's why the system becomes non-equilibrium. Now you can find out energy fluxes in the system by the use of stochastic thermodynamics, and you can take the total derivative of the earlier Hamiltonian, and you can write them in terms of the moments sigma x and sigma v, which are defined over here, and you can recognize them as the rate of work done and the rate of heat exchange by the particle with the bath. Okay, but this q dot, which is the rate of heat exchange, is the thermodynamic heat only if there exists an engine with equilibrium bath with the same energy fluxes, which means that you can have such kind of a mapping. Okay, so now we want to establish under which conditions this q dot turns out to be a thermodynamic heat in the thermodynamic sense. Okay, so in general, you can define the efficiency as the work output divided by the Q absorbed by the particle. And if you try to find out over a cycle of period Tp, then this will be the general definition. And so this the cycle would consist of typically of two isotherms at two different temperatures and two adiabats. Okay, so usually as the Carnot kind of an engine. And if you can define this mapping from non-equilibrium to equilibrium, then the efficiency of your engine, it will be 1 minus T effective minus divided by T effective plus, where these two isotherms in presence of this non-equilibrium fluctuations will correspond to some temperatures T cold and T hot, but the effective temperatures can be completely different, and you may get efficiencies which are higher when the mapping exists, which are higher than the usual passive efficiencies. Okay, so what we do is, in general, we start with the system which is driven extremely slowly. So what it means is that the rate of change of this KT is much slower than the relaxation time of the system. And what we find is that in general, the dynamics of the moment sigma x and sigma v can be given by an equipartition theorem, where the temperature in the equipartition theorem is changed by the T effective that we have in the system, and a virial theorem. So it's a combination of these two theorems which tells us under which conditions the T effective can be defined, or a mapping from non-equilibrium to equilibrium baths can be done. So this is the general way. So you start with the Langevin equation, as I have described earlier, where F is this friction kernel, and then you multiply this equation by the velocity and this equation by x, rearrange certain terms, and adding them, what you get is basically the rate of change of this position velocity correlation minus k sigma x is the, again, the moment of x to the power n. Sigma v is the second moment of the velocity, and another term which is basically the addition of this force, noise, and its correlation with the position. Okay.
So now can we go to like 3 minutes to the end?
Sorry.
Like 3 minutes more.
Okay, sure. I should be finishing. Okay. So this F total is nothing but this quantity, and now if you want this to have equilibrium mapping, then the contribution from the virial of the bath, which is this friction kernel plus the active noise into the position, and if you find the, so if the virial contribution of the bath is completely uncorrelated with the position of the particle, then only such a mapping can exist. Okay. So this is a general way of solving this. So I will not go into the details. This is a very straightforward way of doing this. But we can consider particular examples, which are very, very popular example in the active particle community. And one of them is basically the active Ornstein-Uhlenbeck process, right? But in the underdamped regime. So eta correlation is given by this exponentially correlated function. And if you in general find out this virial contribution and its correlation with the position, then in general this this contribution is not zero. Okay, so for such a simple system, which is very popular in studying Brownian motion, active Brownian particles, there the T effective does not exist. Okay, so it only exists in certain limiting cases where this U is zero, or this dr is very, very large, or the trapping strength K is very, very large as compared to these two terms and so on. So only in such limiting cases this exists. The next example that we consider is that this eta correlation is exponential and plus a thermal noise added to it. So you have a normal thermal noise, and then there are active particles inside the bath which have this kind of correlation. In that case, you can fine tune your parameters to get a T effective, and in general, T effective will not exist. So I will just plot a few. So only at this point, where all these three graphs basically match, you have a effective temperature, and nowhere here there is no effective temperature. Similar to equilibrium cases where the if temperature or due to the equipartition theorem will be related to your kinetic, the trap strength. Here the T effective also depends on the trap strength. And with this, I would like to conclude. So this mapping is important to call machines in contact with non-equilibrium baths at heat engines. We showed that a class of underdamped active engines allows such mapping if the total force exerted on the particle by the bath and the particle position are uncorrelated. It is always fulfilled if the friction kernel and noise autocorrelation function in the Langevin equation are proportional to each other. I mean, so the effective, it's kind of an effective variant of the second fluctuation dissipation theorem. Where this proportionality is broken, you can fine tune your parameters, and the T effective may exist. In general, it does not. And we believe that this validity of this condition can be checked in experiments. I don't know how easily, and we can extend our analysis to non-casuistic regime. Power delivered is non-zero to higher dimensions and complicated potentials. And with this, I would like to thank you, and I would like to answer your questions if there are any. Thank you very much.
Thank you very much, Rahul. So let us go indeed to questions. Time is now or later, but yes, please. Urna?
Yeah. So Rahul, you had in the last slide or the one before where you were doing this underdamped AOUP.
Yeah.
So this eta noise, Do you also have a dynamics for that? You assumed a 2-point correlation, but is it also Gaussian?
I mean, can you see the screen?
Yes.
So
yes,
this one?
The one before?
Yeah, so we did not really consider
value model.
Or this one?
Yeah, just the one before.
Yeah, so I mean, you can.
Where you wrote the.
Yeah, so here in general, I mean, this eta, you can define another Langevin equation, right? Which eta dot with minus tau a or something like that. So that is all right. But even then,
that's what you.
Yeah. So I mean, if you want to simulate it, you would do basically something like that. But even then, you will be able to show that there is no T effective.
Okay.
Okay.
Yeah.
Okay, so you're really asking that the force is uncorrelated with the displacement of the particle, right?
Yes.
That's very strong, of course,
yeah.
which would maybe lead to things like mobility being proportional to the diffusion constant, but it would not be something you expect genetically at all.
Yes, that's right.
Are there other questions?
Okay. Yeah.
Other questions? Not here. So thank you again, Rahul. And maybe we can go to the next talk, where Ion Santra is here to share the screen. Ion?
Yeah. Hi, Chris. Hi. Thank you.
Hi, Ion.
So can you hear me? Can you see my screen?
We can hear you, but the seeing, there it is. Okay, great. Thanks a lot. So please go ahead.
Okay. Thank you, Chris, and thank you to the organizers for giving me this opportunity to talk. And so today I'll be talking about a recent work done with Urna Basu, which can be found in this archive. And it's the title is Activity-Driven Transport in a Harmonic Chain. Okay, so let's start with a little brief background on transport, thermal transport especially. So people have been interested in thermal transport from a long time. So the basic idea behind this is you have two reservoirs, one at a hotter temperature and one at a colder temperature, and you connect these two with some intermediate medium, say for example like a rod. And then people are interested in questions like what is the energy current flowing through the system from left to right, what is the local temperature at each point in this medium, or what is the conductivity, etc. So of course empirical laws like Fourier laws were known, but the first some real analytical insight into this was given by this seminal work of Ryder, Lieb and Lebowitz in 1967, where they took a harmonic chain, and at the two ends of the 1D harmonic chain, and then at the two ends of the harmonic chain they connected two different thermal baths at different temperatures, and they found some interesting properties which actually violated the Fourier's law. So what they found is the system reaches a non-equilibrium stationary state, which carries a thermal current which is proportional to the temperature difference at the two ends of the temperature difference of the reservoirs. And they also showed that this system reaches a local equilibrium with a well-defined local temperature at each site. And the bulk temperature was actually flat, and it was basically given by the mean of the temperatures of both the reservoirs. Okay, so over the years, several generalizations of this simple model has been done with disorder, pinning, activity, pumping, etc. in the bulk. But the most important thing about all these is the reservoirs used there were equilibrium reservoirs, where the random and dissipative forces exerted by them always satisfied an FTT. Okay, so all these other works which I said can be found in this review and this book. Okay, so now the other part is active particles. Active particles, people have already talked much about active particles, but still to say a line, active particles are basically self-propelled particles like bacteria or genus beads, which can generate dissipative persistent motion, and they are inherently out of equilibrium, and they do not satisfy fluctuation dissipation theorems. Okay, so these are very common in nature, and advancement in microrheology have triggered experimental and theoretical works in the last decade, which have basically studied the dynamics of a single probe particle in a pool of active particles. Okay, so this Maggie et al. In I think 2015, and this PRL paper showed that the effective dynamics of a single, like this probe particle in a bacterial bath, can be described by a Langevin equation, which has with an exponentially correlated noise. Okay, now standing here, one very obvious and important question would be to ask how the transport properties of an extended system would be affected if they are connected between two active reservoirs. Okay, so in this work, we have basically tried to answer this question, and the best way to answer this question is going back to a harmonic chain. So we consider something which is similar to the RLL model. We have a harmonic chain, and the two end particles are connected to two active paths, and we model the coupling to the active path by including a correlated stochastic force, these Fs. So these are the equations of the path particles, I mean the end particles. So we include this by this correlated stochastic force F, I mean, in addition to the usual thermal component, which is given by these xis. Okay, so the xis are basically the thermal components, the usual thermal components, which satisfy the fluctuation dissipation theorem, while Fs, they do not satisfy the fluctuation dissipation theorem, as you can see, and they have an exponentially, okay, so this would be T minus T prime, I apologize. So they have exponentially decaying correlation. And one example is to consider a dichotomous noise, which flips between +1 and -1 at some constant rate. So this is important as we have considered to this for our numerical simulations, which validate our analytical results. Okay, and also it should be mentioned that the bulk oscillators, other than the boundary ones, they are completely Hamiltonian, energy conserving, and this is simple Newton's equation which describes them. Okay, so basically I'll be talking about the two quantities of interest which we have shown in this paper, which is the average stationary current flowing through the system and the average kinetic temperature profile of each site in the system. Okay, so let's start with the average stationary current. So the average stationary current, using these equations of motion and these correlations, it turns out that it breaks into two parts. So one is the thermal part and one is the active part. So the thermal part is exactly same as the one obtained by Rydell, Lieb, and Leibowitz, proportional to the temperature difference, the thermal temperature difference between the two ends. And so for the following discussion, I'll keep the T1 and Tn, the temperatures, to be 0 at both ends, and then we have this active part. So the active part has a very nice expression when we in the thermodynamic limit, which this nice closed form expression, and also this nice closed form expression exhibits some wonderful features. So first of all, as you can see, this is the plot for the active current. It increases and against one of keeping one end activity of one end constant and varying the other. So you can see that this active current increases, it hits a maxima and then comes down again and goes to some constant value. So it's non-monotonic, which gives rise to a negative differential conductivity. And another interesting feature is this active current actually crosses the zero line twice. So it reverses its direction twice. So one you can trivially guess when the activities of both the reservoirs are same, that is τ1 equal to τn. And there's another 0 point for the current, which at some non-trivial value, which is actually given by this red line. And this is how the phase diagram of the current in the activity plane. You see the τ1 equal to τn line, and this line they just divide it into regions of positive and negative current. Okay, and this can be somewhat explained if we assume that the current is an effect of the overlap between the spectrum of the system and the spectrum of the reservoir, frequency spectrum of the reservoir. And then if you look at the individual frequency spectrum, and then if you look at the overlaps, and you would see that this overlap is actually also non-monotonic, which in a way causes this non-monotonicity of the current to occur. Okay, and then also the differential conductivity chi j which becomes negative at some points. That is basically nothing but the linear response of the current to a small change in activity of any one of the reservoirs. Okay, so one can do a linear response calculation and arrive at a linear response formula. Of course, this formula is for a particular chosen set of a particular realization of the noise, and this one corresponds to the one I showed for the dichotomous active noise. And we find this nice looking formula which says like, yeah, so the number of flips, when this number of flips is positively correlated with the current, this one is this differential conductivity is negative.
Like 3 minutes, Ion, is okay?
Yeah. So then I'll talk then kinetic temperature profile. So what we see is the bulk profile is flat, and it can be cast in a form similar to which is this mean between curly T1 and curly Tn. There's a non-flat boundary layer which is exponentially decaying, and the profile is not completely flat even when tau1 equal to tau n. And the boundary kinks, which are popularly called contact resistances, vanish for strongly active oscillators. Okay, now the form of this bulk current, it raises a question that because it looks similar to the RLL in a way, so it raises a question if we can associate effective temperatures is curly T1 and curly Tn to the active reservoirs. But if you want to do that, it turns out that this is not consistent. So if the activity of the reservoirs are same, for example, say T1, say curly T, and then you see the bulk follows the zeroth law, so it's still T, but the boundary layers are not T, so it's not flat. So the zeroth law is not followed everywhere. And secondly, the stationary active current, which would have been generated if the system were connected to thermal reservoirs of temperatures curly T1 and Tn at the two ends, is quite different from the actual active current we are getting. So mathematically, this J active curly T1 Tn is not in general equal to curly T1 Tn, but there's an effective thermal temperature when both tau1 and tau n are very small, which we can see. So in this regime where both tau1 and tau n are small, this brown curve, so this dashed line and this one coincides, almost overlaps. So that is the region where we have an effective thermal picture. So summarizing, we studied the transport properties of a harmonic chain coupled to two active reservoirs, which exert exponentially correlated stochastic forces. The coupling leads to a non-equilibrium stationary state, which carries a current that exhibits NDC and current reversal even in a linear chain and without any kinetic constraints. The temperature profile is uniform and can be cast in a form similar to thermal reservoirs, but no effective temperatures can be consistently built. And the analytical results we have obtained, of course, in the thermodynamic limit, are robust because these exponential correlations are seen everywhere, as you saw from the previous talks also. And some important feature detections would be to look at the effect of disorder and harmonicity, pinning, and all the other things. And also, if we could consider some explicit analytical model of the active reservoirs, like this Onupom's active chain, and look if how these things are actually, if these things are changed or not. Okay, so thank you.
Thank you very much, and such a nice picture. Thank you so much, Ion, for these really exciting facts and phenomena. Are there some quick questions here? Abhishek, please.
Yeah, hi. So, and maybe you already said this. I mean, so even when like you get when the current is zero, even in that case, you're saying that it's you can't think of it as some effective.
No, see in this plot, see this the yellow one. It's also. I mean, it should have been. I mean, if we could think of it like that, then the yellow one should have been flat, I guess, right? Because the activities at both ends are same.
Activity, but is this the case with zero current?
Yes. So this is zero current.
Oh, that is.
There are two places of zero current, right? One is where the activity are the same, and the other one is well, where something else is true. You don't have this on the screen, I think, no?
Okay.
So yeah, this one. So the red ones are basically the non-trivial zeros, which is a very complicated expression, but this is how it looks kind of in the tau1 tau n plane.
it's like a zero current non-equilibrium situation where there is just activity but no directed motion.
Yeah. Okay. Yeah.
And of course, the steady state is always a Gaussian, right? But it's
yes,
not...
the velocity. Yeah. I mean, if you look at the velocity distribution of in the bulk, it's a Gaussian. Yeah.
It's a Gaussian. Okay, but some correlations will show that it's not equilibrium.
Yes. But yeah, we don't really.
Yeah, thanks.
Well, I mean, equilibrium you cannot quite see from just the distribution, right? I mean,
okay. You're saying from the steady state distribution, there's no information on.
Well, okay, there is, but it's not sufficient, maybe. Are there other questions?
Okay, yeah.
And Junaid has raised a hand.
Yeah, by the way, I didn't quite see it, but did you also look at least simulations in the exponential case? I mean, where you do not have quite the RTP type noise, the telegraphic.
Yeah. It works for ABP kind of noise also.
What you showed, okay.
Yeah. I don't have it here, but I mean the current is exactly like this.
See it here, yeah. Okay, but you have, it's not only for the RTP, right?
No, not for RTP. For the APB case also it works out.
That's really very nice. Opening new chapters in theory of conductivity.
I had one question actually in the graph that I was showing.
Yeah. Which one?
Yeah, this one do you have any physical understanding like why you get the zero current for tau1 not equal to tau1?
No, not yet. No.
Okay.
You can also ask the opposite question. Why do you have a current at all?
Yes.
So it may be the opposite, which is the more strange thing. What is being transported? Yes. Well, energy, but I mean, what is the picture?
Yeah, I mean, so like if you think of the active, I mean the particles like some batteries or like these hex bugs or something, they're I mean they're pushing each other or something like that, maybe.
Okay, so we will see more of that, I'm sure.
Junaid, I think, also has a.
Oh, sorry. Yes, please, Junaid. Yes.
Hi, Ayan. So I had this quick question. So does the boundary conditions play a role in this situation also in the active current?
So, I mean, boundary conditions as in what else you want to use?
I mean, the free and the fixed boundary conditions. You probably have fixed boundary conditions.
Yeah. No, free we haven't.
They play a role with the other part of the current. So do they play a role with the thermodynamic limit? I mean.
No, we haven't seen. I mean, we haven't checked.
Okay, thanks.
Yeah.
Okay, I think it's probably time to close that session here. So thanks to all the speakers for really very interesting talk. Thank you. Organizers, I think it's time also to move to breakout rooms. Is that
breakout rooms? Yes. There's a room for every speaker. So I request all the speakers to wait for a few minutes to their rooms, and